Hello everyone, welcome back to Pallence AI. In the last video, we looked at the intuition behind a simple deep learning algorithm, how information flows forward, how we compute the loss, and how we use gradient descent to update the weights to train a simple deep learning model. All through that explanation, I kept using one word or maybe a variation of the same word again and again. That's weights or coefficients or parameters. In today's video, I want to zoom in on that idea. What are these weights exactly? Why are they so important? And why do you keep things hearing like, this model has a billion parameters, the GPT-5 has trillion, or Gemini has trillion? What does that really mean inside a neural network? I'm going to explain it in a very simple, easy to understand fashion. Again, the example we're about to see is similar to what we used in the previous video where I explained the intuition behind a deep learning algorithm. And it's also the same example I use in my deep learning mastery course on Udemy. So we use a small neural network that classifies handwritten digits to show you how many weights it has, how to compute them, and how the same idea scales up to very large models. Even though the example we're going to see is from computer vision, the logic is the same, whether it's speech models, or for large text models, language models like GPT. At the end of the day, every deep learning system is trying to learn the right set of weights that connects our input to the output we care about. Again, if I can repeat, deep learning is all about training a model that can find these optimal weights or parameters that can map the input data to the output that we're trying to predict. It's that simple. All right, let's jump into the lesson and take a closer look at these weights or parameters. Okay, let's look at the weights or the parameters that the model is trying to learn. Let's again look at a shallow machine learning algorithm like logistic regression. We have already seen the intuition behind how a traditional machine learning algorithm works in the previous video. Bottom line, it's trying to map X and Y, right? Trying to come up with a mathematical relationship to predict Y given X. Something like a linear relationship first between the weights and the input X, right? And then on top of it, it applies a function F to calculate Y pred. Okay. So for a simple machine learning algorithm, when we are saying weights or parameters, right? They are W1, W2 up to W784, and then a bias term B. So the total number of parameters for this algorithm would be around 785, right? Simple enough. Now let's look at the weights or parameters for a deep learning algorithm. We have already looked at the intuition behind a deep learning algorithm for a two-layer neural network, right? In this situation, one layer being the hidden layer, right? Where you transform the input data into output units in the hidden layer A1 to A512. And from there, we're going to have one more final layer, which would be the Y pred layer with 10 classes here. Again, this was like a multi-classification problem we looked at earlier. Right? Okay. So now let's see how the equations look like, right? We're trying to find the hidden units, the outputs in the hidden layer, A1, A2, up to A512, using the input pixels from X1 to X784 and the weights. So let's see. So we're going from X to Y. So let's look at the output layer, right? For the hidden layer, output units for the hidden layer. So again, you can express each hidden unit in the hidden layer, A1 to A512, as a mathematical relationship between all the input pixels X1 to X784 and these weights. So A1, you first calculate the linear relationship between the weights and the input pixels and add the bias term, and on top of that you apply a function called activation function F, okay, and you calculate A1. Similarly, you calculate A2, A3 up to A512, okay. So you can express this in terms of matrix notation. So you can express capital A to represent the output, of the hidden layer, A1 to A512. Okay. Again, as you can see here, A, capital A equal to a function of, right? It's a matrix multiplication between input X and the weights, first set of weights, W1, and then the bias term. Okay. So this is how you calculate the output of hidden layer A, capital A. Then you take the output of hidden layer A, right? And again, as you can see here, with the blue lines now, each hidden unit is connected to each output unit in the Y pred, right? So similarly, you can calculate the output of each unit in the Y pred, right? You connect it with every hidden unit in the hidden layer
and you come up with a mathematical formula, relationship, basically linear relationship first, and then on top of that you apply a function f. Basically that would be an activation function, and you calculate y1 pred. Okay, so again y2 pred, each output in the y pred final layer is connected to every hidden unit in hidden layer L. So this type of connections, what you're seeing, where every unit in a subsequent layer is connected to every unit in the previous layer, these are called dense neural networks. Dense models, dense neural networks. Later in this course, we're going to look at more complex neural networks like CNNs or RNNs or transformers. Okay, but for now, the intuition we covered already, it shows this kind of a connections where every unit is connected to every other unit in the previous layer. These are called densely connected units. Okay. All right, but this is good enough for us to understand the intuition and also to see how what these weights look like. So as you can see here in layer 2, right? So which is our final output layer, we are calculating y1 pred, y2 pred, and up to y10 pred. So this can also be expressed as a in the matrix notation. Y pred is equal to again a function applied with a matrix multiplication between A, which is output of hidden layer, and the second set of weights, again the first set of weights are in pink, and the second set of weights are in blue. So W2 would be the second set of weights, and then a bias term. So you apply activation function f to that, and you calculate y pred. Okay, so now if you look at these equations, you can clearly see what kind of dimensions the weight matrices have. So again, for the first set of weights between the input layer and the hidden layer, right, we call them like W1 IJ basically. So it's a 784 by 512 matrix, the weights. And similarly, we have the bias term from B1 to B512, right? Again, these are the first set of weights in pink. Okay, so the second set of weights would be W2. So these are the weights between the hidden layer and the final output layer y pred. Right, so W2 is again a 512 by 10 matrix, right? Similarly, we have the bias terms, again we call it B2. So if we want to see the total number of parameters, again for the first set of weights, right, W1, it's a 784 by 512 matrix. So we have 784 times 512 plus 512, the bias terms will give you a total number of parameters of 401,920 approximately for this first set of weights. Similarly, for the second set of weights, because W2 is a 512 by 10 matrix, so 512 times 10 plus 10, 5,130. So in total, right, for this simple neural network, which we have used to explain the intuition behind deep learning with two layers, one would be the hidden layer and then the final output layer. For the simple neural network, we have a total parameters of around 407,050. Right. So now if you're wondering, wow, this is large, right? 400,000. Well, if you heard about, one of the latest or, one of the large language models, right? You have been hearing about all these AI models, LLMs in the literature, in the industry, right? So one of the earlier, language models like GPT-1, that model was like a 110 million parameter model. Then came another natural language model, BERT, right? That was around 340 million parameter model. And from then on, it was an arms race, right? It was a race between many different companies and research groups to come up with larger and larger AI models, particularly LLMs, large language models, up to the latest, with ChatGPT, which is powered by GPT-4, it's around trillion parameter model. Right, whether it's Gemini or Cloud, they're almost all touching 1 trillion parameters. So now whenever you hear about all these latest AI models, whether it's a computer vision model or a natural language model, a large language models, right? When you're talking about the parameters or weights, this is what they're talking about. So the intuition is the same. Right, so this is a simple neural network with two layers, right? Just one hidden layer basically, and you have around 400,000 weights. So it's the same logic with all the latest AI models. So these either it's a machine learning, simple machine learning, or deep learning, or complex large language models, right? What they're trying to do is they're trying to feed on vast amounts of data. Lots and lots of data. You can call it input X, right? Looking at lot of this data, the deep learning models or the language models or the basically AI models, they're trying to form complex mathematical relationship by calculating these optimal weights or parameters, right, which can help these models in understanding, many types of diverse, statistical and structural patterns between vast amounts of data which they have seen, and in the process they become smarter. Once they calculate these weights, the models we say that they are learned, right? They're pre-trained models. So then you give these models some new data and they can perform like magic-like tasks, whether it's a computer vision or natural language processing. And today we are seeing with ChatGPT, it almost feels magic, right? It's like the AGI, but at the end of the day, when it comes to deep learning, which is again the foundation for all the latest AI models, right? All they are trying to do is look into vast amounts of data. If it's language, they are going to look at vast amounts of natural language, like, corpuses, Wikipedia, internet. If it's image models, they're going to look at lots and lots of images, right? Like what we've shown here with a simple example. So they're going to feed on a lot of input data X, and it's just going to try to map it out by coming up with this optimal mathematical relationship. And when we say mathematical relationship, right, what defines a mathematical relationship? It's these weights, these parameters, which is pretty much, the main thing, when it comes to a deep learning AI model. Okay, so now you have a better understanding as to the intuition, right, as to what these weights and parameters are. Next video, we're going to look at more interesting concepts. For example, F. What is this activation function, right? Why are we even applying it? Similarly, what about this loss function? We said the loss function calculates the error between y pred and y, but how does this loss function look like? What is this optimizers? We hinted that optimizer is based on gradient descent, but what exactly is gradient descent? So we're going to look at many more interesting things in the next videos.
Okay, thanks for watching. I hope this video helped you in understanding the weights or the parameters inside a deep learning model or neural networks a little bit more clearer. This lesson is again, the part of my deep learning mastery course on Udemy, and have provided a description. If you would like a more structured end-to-end path with all the hands-on projects included. But again, if you found this video helpful, please feel free to subscribe so you don't miss the next valuable concept as we keep building our AI foundation in a step-by-step fashion. I will see you soon in the next video. Happy learning and thanks for watching.